Uh, Today's LeetCode daily challenge is question number 137, single number 2. The, the problem description is that given an integer array named nums, where every element appears 3 times except for one element which appears exactly once. So our goal is to find the single element that only appears exactly once and return it. And the requirement is that the time complexity need to be linear and the space complexity need to be constant. The topic involved, which can be shown in the problem description here, related topics, is bit manipulation. So bit manipulation is basically, or in brief, is to use uh, some bit operation to minimize the memory or the calculation we normally would in general approach. So for a decimal number like 37, we can find the binary representation. You can easily find it if you if you don't know how to find it. I put it linked in the description of this video, and you can look to the first reference. And basically, like for decimal, it is represented as the of multiples of the powers of 10, like 37 equals to 3, 10, 10 to the powers of 1, and 7 times 10 to the power of 0. So similarly, we can find the binary, which is the representation in the base of 2. Okay, so from the least significant bit all the way to the most significant bit. So so the question here is that how do we find the third bit of the binary representation of 37? So the answer is to right shift the number. The original number is 01000101, and we right shift the number by 3 bits and take a bitwise AND operation upon the right shifted number and 1. So the first the first step is to right shift the number 3 by 3 bits. So the original number is here, and it will shift 3 bits when we will get here. For the most significant bit, we will pad with 0 to make sure the sign bit is always consistent. After after we right shifted the number by 3 bits, we take an bitwise AND operation with one. So this is the right shifted number here, and we take an AND operation. So since the binary representation of 1 is 0, 0, 0, 0, 0, 0, 0, 1, and since the AND operation between 0 and anything is 0, so we can just fill this blank with 0, and the answer we want will be the binary value of the third bit. Okay. So what's oh how can we apply the bit manipulation to this problem? Let's see an example to find out how can we approach this problem. Let's say we have an array like this. The the zeroth number is 2, the first number is 3, the second number is 3, the fourth number is 3, and the fifth number is 2, and the sixth number is 2. And we represent each number in this array by its binary representation. So 2 equals to 0, 1, 0. So, and since it will appear 3 times, we just copy it to the fifth and the sixth. And similarly, 3 equals to 0, 1, 1. And it also appears 3 times here, here, and here. And finally, which is the only element which appear exactly once, and this is the answer we would like to find. Here, 7, which equals to 1, 1, 1. So if we take the summation, bitwise summation, we can get one from the least significant bit to the most significant bit. Basically, we just sum up this column, so we can get 1 plus 1 plus 1 plus 1 equals to 4. Okay, something missing here. Okay, so this should be also like, okay, this is 1, 1, 1, 1, 1, 1, 1, right? Let's see. Right, all right, so this is 7, and this is 0, only 1 here, so this is 1. So we 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 calculate the bitwise sum of each bit. Okay, and there's need to sorry, need to modify this. 174. Okay. Okay, so the next step after we calculated the bitwise sum, we will calculate the bitwise the module of the bitwise sum over 3. Why do we take modulus over 3? Because if 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 the number appears 3 times, like here, like the red one, the red one is 3, right? So it appears 3 times. So all the contribution to the sum after module will be 0. Like it appears 3 times at a 0 bit, but after module 3, it will become 0. Okay. So after module, we can find that the number after module is exactly the target or the answer we would like to find, which is 7, 1, 1, 1, 1, 1, 1 here. Oh, okay, so the approach is quite simple. First, we want to calculate the bitwise sum of each bit, starting from the least significant bit all the way to the most significant bit. After calculate the bitwise sum, we would ask, what's the what's the what's the result of the bitwise sum after module 3? Basically, what's the remainder after dividing by 3, right? So in this case, we are calculating the bitwise sum of the 0th bit, and since the bitwise sum is this is not 3, this is 4, this is 7, this is 1. Since the bitwise sum is 4, so after modulus 3, it will become 1, so it does not equal 0. So we will add it back to our answer by the 2 to the powers of the bit we are currently at, which is 2 to the power 0. So we will add our answer. Initially, it's 0, and we will add 2 to the powers of 0 to the answer. We want to restore the whole number bit by bit. Okay, so after this, we will examine the next bit, which is the first bit, and again calculate the bitwise sum of the first bit, and examine whether the bitwise sum remainder equals to 0. If not, we will sum it back by like this one. Again, this no 7 4 1 is 4, so the remainder is 1, and we will add it back by 2 to the powers of 1, since we are at the first bit. And next we will examine the next bit. So until we examine to the most significant bit, and we can restore the target number, which is 7. Okay, so what do we have? Let's see. Okay, we'll put our approach here, and first we need to initialize a variable which will record our answer, and we initialize it to be 7, and for bit starting from the least significant to this least significant bit all the way to the most significant bit. And by our definition, the least significant bit is 0, right? Here it's 0. All the way to the most significant bit. So let's see the problem description. So it says that every number, the largest number will be 2 to the power of 31, plus and minus. So we at most need 2 to the powers of. Okay, this is the range of the variables. So we need 32 is because plus and minus right here. 30 bits to represent the number in the array nums. Okay. Right. So this means the most significant bit will be at 2 to the will be 2 to the power of 31, 31, 32. Let's see, 2 to the powers. So this is 2 plus 31. Okay, is that true? Okay. 32, 31. Is that right? Okay. So beat the bit from least significant to most significant will be from 0 to 31. And after we examine each bit, we will examine the next bit. We'll add it by 1 bit plus plus. Let's see. Okay, so the first thing is that we want to find the bitwise sum. So we will declare a bitwise sum, equals to 0, and we want to find the bitwise sum. So the bitwise sum over all numbers, right? All numbers. So the numbers in the array names is nums. Okay, for number constant, okay, int numbers in the array, what do? We add it up, right? We add it up, and we only added up the kth the bit, okay, the current bit, right? So the current bit, how to calculate the current bit is by right shifted the number by how many bit we are at, right? The numbers first right shifted by the number of bits, and the second step is to take a bitwise AND operation with 1, okay? And the take bitwise AND operation with 1, and okay. Okay, so we summed it up. After we summing up, calculate the bitwise sum at, okay, this is kind of baffling. That will be consistent with the description here at the kth bit. Okay. After calculating the bitwise sum, we will examine whether the bitwise sum of the kth bit, okay, we will ask if the remainder equals to 0, right? So we take module, wait, this one, okay, bitwise sum take modulus over 3. Is it 0? Okay, because it's a binary, right? So the after module there's only how many possibilities that there can be 0 possibility. A possible outcome is 0, 1, or 2, right? Take a modulus over 3. So let's see. Modulus. But since all a number, either suppose we have like n, suppose we have n equals to the number length, right? It's okay, back to size. Okay. So, uh, so there will be a m plus 1 element which appear 3 times, and one element which that appear ex exactly once. Okay, so each of sorry, my English, that appears 3 times. So for the m minus element, after module, the contribution will be 0, right? The module will be 0, and the contribution of the only element that appears exactly once will be 1. So the possible outcome is not 1, 0, 2. It will be 1 and 0. So if it is 0, then there's nothing to add. If it is 1, then we will need to add the answer by 2 to the powers of k. Okay. Okay. And after we examine all the bits, we can return the answer. Let's run it to see if it. What's the problem here? Let's see. That's expected expression. Let's see. This one for int k plus plus. Sorry. For what's the problem here? Let's see. Okay. Character expected expression. Expected expression. K minus 32. Okay, this one. K minus. Oh, what the fuck. Sorry for the answer. Wrong answer. Sorry. Let's see. What's the problem here? For each bit. Okay. Numbers. Right shift. Okay, we output byte 2. If bitwise sum module, we add it by, let's see, numbers. Okay. What did I miss? What did I miss? And 1. Okay. Each number. Okay. Right shift. Bitwise sum equals to expected is 3. Let's see. K equals to 0. We need to print some output here. Plus 1. What should I how to say? And plus 1. Okay. Do you have it? Why? Okay. Let's put out some outputs. Sorry. Okay. Just wrong simple example. Okay, let's see where did it when did it go wrong? K equals to 0. Okay, 2232. Okay, 2232 will be like 2232. The first number is 2232. The bit 0 1. Okay, 2 to the power. Okay, this is 1 0 1 1 0 1 1 1 0. So the bitwise sum will become 1 2 3 4 5, and this bitwise sum is 1, and after module it will become module 3, it will become 2. Okay, 2. No. This is the first bit. This is sorry. 1 2 3 4. Is it 4? It's 1. Okay, 1 1. Right. So k equals to the 0th bit. Answer equals to 2. Answer add by 2 to the powers of k. Okay. K equals to 0. Why? Answer starting from 0. Okay. Let's see, 2 to the powers of 0 is rounded. Character string. Two. Okay, so this is a problem here. How about B? 2 to the powers of 1. Better be. Need to review the expression of power in C++. Okay, why? 2 CBP power representation. The exponent value is calculated using a power function. But okay, so here it is not to the power, it's like maybe some bit operation. Another way to do this is just let's see, a remainder. We just code a remainder to be the okay, and we will use it remainder and shift it by k, right shift it. So it's equivalent to adding the answer by 2 answer plus by 2 to the powers of k, right? And see what it'll be correct. Okay, I submit it. Alright, sorry. Oh, that's it. Beat only 28%. Okay, quite miserable. Anyway, that's it.